So, dear students, today we will discuss about the basic about the FFT algorithms. Now, in DFT algorithms, DFT stands for, as we have already discussed, DFT is discrete Fourier transform. So, this is discrete Fourier transform, and DFT of any particular sequence is done by or through direct computation. So in direct computation, what is the limitation? The limitation is that it requires a large number of computation, large number of iterations basically. So to perform the large number of computation and iteration, we need large processing time. Okay, and also we need the processors of high speed and high capacity. So this is one limitation of DFT, or you can say this is one such fact about DSP, which has led to the development of some fast algorithms, which we also call as fast Fourier algorithms or fast Fourier transform algorithms, which we will be discussing in today's lecture. Now, for any endpoint DFT, basically, for any endpoint DFT, there are, let us say, n square, n raised to the power 2 complex multiplications are required. Okay, and similarly, if we talk about the addition, so the addition is n square minus n complex additions are required. So this huge amount of computation or mathematical processing is required uh, in case of what do you say, the DFT, right? Okay, so now so you can see that this huge amount of computation is required in DFT, and this huge amount of computation lead to the large processing time, and it also needs large processors and high capacity processors. So as we can see that if the value of n is large, then the number of computations will also go in lakhs, right? So this is what we can say that is the one of the drawback of DFT. So what happened in 1965, Cooley and Tukey, they developed a very efficient algorithm to implement the DFT. So in FFT also, which we call as FFT here, like, okay, this algorithm is called as FFT. So in FFT also we are doing DFT only, but in a different way. Okay, it has its own algorithm, its own way to compute the Fourier transform or discrete Fourier transform of the given, uh, you know, system, right? So let us see what is FFT. So now, okay, so FFT is the algorithm in which we can uh, number of arithmetic operations which are involved are reduced. So this is an advantage. Okay, this is an advantage over the TFT. This is an advantage of FFT over the discrete Fourier transforms, because here what we have done, we have reduced the amount of computation. Okay, so and since we have reduced the amount of computation, so it will take less time, right? It will take less time and less processing or capacity to compute the final discrete Fourier transform. Okay, so there are different FFT algorithms basically, and out of which we have Radix-2 FFT algorithm is the most important FFT algorithm. So there are various FFT algorithms. So this is the mostly used FFT algorithm, right? Now let us see what is this. Okay, so what is a Radix-2 FFT algorithm? So a Radix-2 FFT algorithm is basically uh, an algorithm in which we can solve, or we can find out the endpoint DFT of the given sequence, given signal, right? Okay. Now, if we have endpoint DFT, so we can factorize this n into, let us say, R1, R2, R3, and RV. Okay. So where R is a prime number, right? So if R1 is equal to R2 is equal to R3 is equal to RV is equal to, let us say, R. So we can write n is equal to R raised to the power V. Okay. Right. This is called, this R is known as radix, means base. Radix means base of the FFT algorithm. And V indicates the number of stages in FFT algorithm, right? If it is 2 raised to the power 3, then the base is 2 and number of stages that would be used to find out the final Fourier transform is 3. Okay, so that means that particular sequence will be solved in 3 different stages. And the concept of stage will also be discussed, right? Now, okay, so let us come further. Now, radix means base. Radix means base. So radix means base. So we can say that if its value is 2, then this is what I discussed just now. Then it is called Radix-2 Fft algorithm. This is what we are discussing, Radix-2. Okay. So that means n is equal to 2 raised to the power V, right? So now if we are computing an 8-point DFT, if we are computing 8-point DFT, so that means we can find out the value of V. So V is number of stages. How will we find out V? So 8 can be also written as 2 raised to the power T, which is equal to n. So here n is equal to 2 raised to the power V. So it is 2 raised to the power 3. So we can have V is equal to 3, right? So that means if we want to compute 8-point DFTs, then we need to compute it through 3 stages of the FFT algorithm. We will require 3 stages of the FFT algorithm, right? Specifically this Radix-2 algorithm, right? Now, okay, so while computing the FFT, divide number of inputs sample by 2. So how this is done, that we will discuss, right? We have to divide the number of samples by 2. So we'll see how it is divided. How do we do that particular thing till you reach the minimum 2 samples, right? So this is the final destination. Based on the division, there are 2 algorithms. Means this Radix-2 is further divided into 2 sub algorithms, which are decimation in time and decimation in frequency, DIT algorithm and DIF algorithm. So that also we will see what is this DIT and DIF algorithm. Now let us come further. Okay. Now, before studying these algorithms, we will desire some important properties of Twiddle factor. Now, Twiddle factor is very important factor which will be required in computing the endpoint DFT of the given sequence using FFT algorithm. We have FFT algorithm. So the important algorithm is Radix-2 algorithm. And in Radix-2 algorithm also we have further 2 sub algorithms which we call as decimation in time, means Radix-2 decimation in time algorithm and Radix-2 decimation in frequency algorithm, right? And in both the algorithms, we will need one factor which we call as Twiddle factor. So this Twiddle factor is basically given by this equation. So this is Wn, it is given by W raised to base n. So this n indicates that n point. Okay, for example, if you are computing 4-point DFT using FFT algorithm, so this would become W4. If you're computing 8-point, it would become W8, 2-point W2, right? And this is equal to exponential of minus j2 pi n, where j is a complex operator. Right. Now, okay, so it has certain characteristics, certain properties that we will discuss now. So in the first case here, we are just checking whether this Twiddle factor is periodic or not periodic, right? So let us take that the Twiddle factor raised to the power of k, and then after some n points, because we are computing n point DFT. So after n point, whether it repeats itself or not. Okay, so we have taken wn k raised to the power k, sorry, wn raised to the power k plus n, which is equal to wn k into wnn, right? So this can be solved in this manner. So we will replace w with exponential e minus j 2 pi n and this one, right? And then we will solve it further like this. So we also know that e raised to the power minus j 2 pi is cos 2 pi, because we know that e raised to the power minus j theta is equal to cos theta minus j sine theta, right? So by using this polar representation, we have got that e raised to the power minus j 2 pi is equal to 1, because cos 2 pi is 1 and sine 2 pi is 0, so it is equal to 1. So that means we will replace this particular part. We will replace this particular part. Which one? This one. This part with 1, right? So what we have got? We have a omega and so wn k raised to the power n in is equal to this one. Now what we can do is we can separate it in this way. Means what we have done, we have taken this k external. So this is the power of exponential. It is like this: e minus j 2 pi by n into k. So we'll take this one separate, and we know that this is equal to wn, and then we have the k power here. So that means this is the final condition. So what it shows that after computing n points, the Twiddle factor repeats itself. So this shows its periodic nature. Now in the second case, we will see whether the Twiddle factor is symmetric or not. So this is to check the symmetric property of the Twiddle factor, right? Now, to check the Twiddle factor symmetric property, what we have done, we have written an equation here, and we have taken that if this equation is satisfied, we will say that the Twiddle factor is symmetric. So let us compute this one. So we have wn raised to the power k plus n by 2, and so we have replaced w with e raised to the power j minus j 2 pi by n and raised to the power this one. So we have opened the bracket here, and we have got this equation here, right? So n to n will be cancelled out, 2 to 2 will be cancelled out. So you have this equation now. Now, is this equation can be replaced by cos pi minus j sine pi. So cos pi is equal to -1 minus j into 0, so it is equal to -1. Right? So now, sorry. So now let us see what happens further and how we can say that this is symmetric or not symmetric. So now let us, because this is equal to -1, right? So we will put it here in that equation. So we'll get minus exponential this one. So this equation further is written like this: j2, sorry, uh, let us erase this one. Let us erase this one, and then we have, let us take pen. So we'll write e minus j 2 pi by n and then k. Right, so this is what we have written here in equation number 9. Now in equation 9, the bracket term is omega n. So this particular term is nothing but omega n. So what we have got? We have got omega n raised to the power k plus n by 2 is equal to minus, it's not omega, sorry, it is w base n and raised to the power k. So this shows that the Twiddle factor is symmetric. So that means Twiddle factor is periodic. So Twiddle factor is periodic and symmetric. So why we have taken this one? Because we will require this Twiddle factor in computing endpoint DFT using the FFT algorithms, right? So we have one more property of the Twiddle factor, which is given in point number 3. So in this, we will see that whether this equation is true or not, right? So we will simplify we solve this equation and prove. So omega n by, so this is basically taken as half of the endpoint, DFT. So Twiddle factor is taken for half of the endpoint. Now simplifying this equation, you get e raised to the power minus j 2 pi by n by 2. So this 2 will go up and it will become e minus j 2 pi by n into 2. So this particular part is equal to Wn square, and this is what we have. So these Twiddle factors are basically used. So we can here conclude in this lecture that what we can conclude that DFTs, basically the conventional DFT algorithms which we have, are such algorithms which have which require large computation. So conventionally DFT algorithms or DFT requires large computation which takes a lot of time and also need high capacity processors, right? So this limitation of DFT has been overcome in FFT, right? So what is FFT? FFT is basically the fast Fourier transform. Okay, this is what the lecture was all about. Okay, so FFT is fast Fourier transform. Right, and the major algorithm is Radix 2 FFT algorithm, which further is equal subdivided into DIT, decimation in time, and DI. So Twiddle factor plays an important role in speeding up the, okay, so this is totally messed up here, so I'll remove all this. Okay, so speeding up the DFT computation using FFT algorithm. So this is about today's lecture, guys. Thank you so much.